It's a real pleasure for the board of the Brazilian Society of Microscopy and Microanalysis to welcome all of you to our 28th meeting, which is being held remotely for the first time. Of course, we all prefer to interact face-to-face, but the coronavirus pandemic really changed the world that we knew and it forced us to move to a virtual universe. The Brazilian Society was founded in 1971, so this year we turned 50 years old. So at this moment, you look to the past not only to understand the base of our history, but to build the bridges of the future. We start our journey towards our 100th anniversary with the understanding that we face many challenges ahead. In this complex and ever-changing world, microscopy becomes essential to help humanity face its greatest challenges. Thus, Brazilian society wants its community to be strongly connected, active, and motivated to keep contributing to national scientific advance. Before officially starting our meeting, I would like to thank the efforts of everyone involved, especially all the speakers, inviters, chairs, and scientific committee. Of course, the companies Thermo Fisher, Geol, Leica, Bruker, Tescan, Zeiss, and Hitachi. Celebrate this special moment, we'd like to invite Dr. Marijn van Heel to introduce our open plenary session.
Thank you very much for this invitation to open this first session. I came back to Brazil some 15 years ago for the first time to open just this session in Caxambu. But now it's my honor to introduce Richard Henderson, and Richard Henderson will have the opening lecture. And he and I met probably in the early 1980s, some 40 years ago, when he came to Berlin to use the great microscopes that we had, the first cryomicroscopes, among the first liquid helium microscope, and to take images of his 2D crystals of GCPR, purple membrane. That was actually the purple membrane story was published, I think it was 1975 or 76, around those years first. That was Nguyen and Henderson. And that was the reason that I entered into biological cryo-EM. I was biological EM. I was actually doing EM and even cryo-EM before that at liquid helium temperature. But that was an instrumentalist. So he came to Berlin in the early 1980s, and we were some of the people who were in the lab very, very late, because in Germany you start at 9 o'clock and you leave the lab at 5 p.m. And so there were the guests and there were the fanatic people that worked until midnight. And so we sometimes went off to go for a beer and talk about the future of electron microscopy and single particle analysis and 2D crystal and things like that. So that became a little bit of a tradition. And then the very first big EM meeting that both he and I were was 1985, organized by WACHU, was the Gordon Conference. And interesting was that in those days, I was doing single particle analysis, was doing 2D crystals. In those days, the meeting was 4 days. Well, it was 8 half days, and there was 1 half day devoted to single particles. Everything else was 2D crystals and maybe icosahedral viruses. And if you now go to the cryo-EM conference, the Gordon conference, it's the opposite. It's people doing 2D crystals are the minority. But he moved slowly from crystallographies from the 2D crystals to single particles, and now single particles is the thing. I don't see Richard still. I think he needs to switch on his hardware, microphone and sound. Yes. So the tradition of going for a beer and pizza with Richard happened there. And the last time we did it was in 2017 in New York, after we got the the Wiley Prize, and we shared, and then we went off to a beer. That was lovely. And I was just talking to him. I mean, we both miss very much the in-present. What most I miss are these meetings, talking afterwards to the people with the beers and okay. So Richard was the pioneer of cryo-EM in 2D crystallography, and he is actually the reason that cryo-EM became such a big success. And with that, I think I will give the word to Richard.
Great. So thank you very much, Maren. Yeah, it is true that I spent about 6 years periodically visiting Berlin, sometimes for 3 or 4 weeks. And indeed, Maren and I usually would be the people left in the lab in the evening. And indeed, also, it was all 2D crystals until about, in our case, we switched around about 1995 or 1996, so 25 years ago, we switched from single particle, from 2D crystals to working on single particles, which has been now had a major impact. So today I'm going to share my screen first, and then put up the first.
Wait.
Okay, so it's a great pleasure. I'm in Cambridge in the UK at the moment, and I'm joining you from 3 hours ahead in time. So it's roughly 1 p.m. and I assume it must be 9 a.m. just like that there. So it's a great pleasure to join you at this. I understand it's the 28th Congress of the Brazilian Society of Microscopy and Microanalysis. And today I'm going to tell you about how single particle electron cryomicroscopy has become a very successful method for finding out the structures of molecules in biology. And so now you can do things that you couldn't do by any other method in the past. So I'll give you a brief introduction first, and then show you a few examples of some of the structures that would be impossible to do by any other method. And then in the subsequent part of the talk, I'll go on and say what are the barriers that are preventing not everything can be done at the moment, but there are barriers, how to overcome them and how to go forward. So I'm going to start with this first slide, which Tim Baker, who is now in UC San Diego, Tim and I made this slide for 20 years ago for the International Tables for Crystallography, which had about 88 chapters, all of them about X-ray diffraction, X-ray crystallography, fiber diffraction, but only 2 of the chapters were about electrons, electron microscopy and electron diffraction. And Hua Chu wrote the article about electron diffraction. Tim and I wrote this about electron microscopy. And so for that audience, and maybe for a broad audience of microscopy people, I think it's useful to say, what is electron cryo microscopy? So we picked out 4 examples of pieces of work that neither Tim nor I had been involved with as examples of what people meant by electron cryo microscopy in those days, 20 years ago. And the first panel is a electron micrograph of a cryo-EM sample made by the Jacques Dubois plunge freeze method that I'll talk a little bit about later. And this is the E. coli ribosome that both Marin Van Heel and Joachim Frank's groups worked on a lot and used it to help develop some of the early single particle EM methods. And so that's the micrograph. And then 10 times bigger below it is a 3D model obtained from micrographs like that, about 10 times the magnification. But in that year, the year 2000, this is Gabashvili et al., the best resolution you could get was about 10 or 11 angstrom resolution, so not below a nanometer. That was a single particle example without symmetry. The second panel is hepatitis B virus cores, which have icosahedral symmetry. And Bettina Botcher, who was a postdoc here in Cambridge with Tony Crowther, was interested in developing the methods for cryo and getting them to work at higher resolution for single particles. So she picked this specimen and managed to get it with about 30 electron micrographs taken on film and about 5,000 or 6,000 particles. She managed to get it to 7 angstroms resolution, which was the first time a single particle cryo-EM structure was determined below 1 nanometer resolution. And you can see it's got this virus core, has these spikes protruding from it, and they've got ridges along them. These are little alpha helices. So that's a bundle, a 4 alpha helix bundle protruding from the surface of that icosahedral virus particle. And then the third panel is an example of a higher level of order. So this is a sort of one-dimensional crystal or a helix. And this is decorated filaments, thin filaments from muscle, where you have the thick and thin filaments pulling against one another to give you muscle tension. And Ron Milligan's group had worked on this for many years. And although it's not very high resolution, 30 angstrom resolution, by doing difference methods, plus and minus the different components, they were able to identify at the middle of the filaments, the actin helix in blue, tropomyosin in green, and then the different subunits of the myosin heads that were decorating that filament at that time. Of course, this and all the other structures are now at much higher resolution. And then the last panel is an example of one of the 2D crystals that Marin mentioned in his opening talk. And actually, this was at one stage very dominant in terms of getting to high resolution in the cryo-EM field. But in the end, there were only 10 or 12 structures. And it turns out it's almost as hard to make 2D crystals as 3D crystals. So this is now not so many people working on this. And you can't see any detail in the images. The little undulations are from spot scan imaging, but because there's so many particles, maybe 10,000 or 20,000 molecules in that one view, with contrast that's too low to see, you can, by image processing of the micrographs, diffraction patterns, get a high resolution model. It was at 3.5 angstrom resolution. And you see these little trimers. That's one protein with 3 transmembrane helices and 13 or 14 chlorophyll molecules in the light harvesting complex. That's the main thing you see when you look out and you see green trees growing. This is mainly that pigment. So that's a good overview of what cryo-EM could do. And if you were starting now to write a review, you would probably add another panel to show how valuable electron cryotomography is. And I'll show a couple of slides that about later, just to give an overview of the field. So that was a kind of introduction. So although many people have contributed to this field, and it's really a big field now, starting in 1985, there were probably 80 or 90 people. Now there are thousands of people doing electron cryomicroscopy. So the next slide is a picture of Jacques Dubois, who moved from the Biot-Zentrum in Basel in Kellenberger's group to EMBL in Heidelberg in 1978 to be a group leader to specifically develop methods for looking at frozen samples of water and doing cryo with liquid helium, liquid nitrogen, and so on. And actually, they did have, in Heidelberg in 1983 or 19, they had one of the same lenses that Maren mentioned was present in the Fritz Haber Institute in Berlin, a Siemens liquid helium superconducting objective lens. And actually, I did use that for about a week, but then 6 years in Berlin. So the apparatus that Dubois, Alistair McDowell, and Mark Adrian developed consisted just of a pair of forceps with a little EM grid here, and you put your 2 or 3 microliters of your sample, which could have viruses, bacteria, ribosomes, and then blot it and plunge freeze it into this little chamber of liquid ethane at the temperature of liquid nitrogen, rapidly freezing, no crystalline ice, and then you could look at it and get nice images. And this was a gravity-fed one, and this one is extra fast, being fired by rubber bands when you release the catch. And so really, although there were many people involved in many of the aspects of it, my view is that this plunge freeze method, which is still used now, 40 years later, obviously it's computer controlled freezing rather than elastic band powered, but still it's the method many people use. And one of the first pictures Dubois' group took was this image of the very big 1,000 angstrom adenovirus particles. And then you can see you've had a thin film of ice, it's been blotted. A couple of the viruses, this one has been destroyed by the plunge freezing, this one's falling apart too, this one's partly destroyed, but most of them, 20 or so out of the particles, look quite pretty particles. They've got spikes coming out of them. There's the occasional subunit that's fallen off. And that was published on the front cover of Nature in 1984, so the year before the first 3D EM Gordon conference. And this was really a marker of the promise, because just looking at this, you know it's full of information, you just have to extract it. But it took 7 years from 1984 to 1991 for Phoebe Stewart, who was a postdoc at EMBL with Steve Fuller, to develop methods of processing this. And she got this 3D structure of the adenovirus at about 35 angstrom resolution. So really quite low resolution, but this is very early days now, 30 years ago. And the reason that it's not higher resolution, because there's nothing you did about the images that says it should be low resolution. You can see the images of the subunits a bit blurry, and that's because it's on film. The source isn't very coherent. The detectors are not very good, the film. And so the fading of the power of the Fourier components can be characterized by this temperature factor, the B factor, and that's very, very large. So the X-ray crystallographers like it to be 30 or less. So it's 100 times worse, and that means the resolution is much worse as well. But nevertheless, that was one of the first 3D structures from 2D images. And it took another 20 years, 1991 to 2010, until Hong Cho's group at UCLA took a better image like this on a more modern microscope, high voltage field emission gun, better vacuum, better stage. And now you can see lots more detail in the images of the adenovirus particles than you could see in 1985. And when those were processed, they got, from the same image, they got a structure like this at 3.6 angstrom resolution. So 10 times the resolution in one dimension. So that's 1,000 times more data in 3 dimensions. And then when you look in detail at the densities, you can see strands in the beta sheet are resolved. They can find the carbonyls. You can see the occasional side chain resolved as well. And that was mainly the improvement in the instrument the hardware of the microscope that made that big improvement, although the computer programs improved. Hong Cho's group, they took 1,000 images instead of only 30. So it was just, force of numbers. And then about 7 or 8 years ago now, a new type of detector came in, and this is from work Greg McMullan was the first author of this from our group in Cambridge, where we were evaluating some of the detectors that became available in 2013. This was the detective quantum efficiency at low spatial frequency and at the limiting spatial frequency Nyquist of the detector. That was film, which people had been using since the 1950s. It was still, before these new detectors came in, it was still the best way of measuring the images. And this is direct electron, Thermo Fisher now, and Gatan's direct electron detectors that were CMOS complementary metal oxide semiconductor based, very fast, and you get a movie as well as having a higher detective quantum efficiency. Each of the images you took is in the form of a movie. So any drift, beam-induced motion, small amounts of charging can be processed subsequently by motion correction of the movie. And so you get a double advantage from these detectors. And so now I'm just going to show you the difference between before and after these detectors from a few samples that became tractable once this technology was available. And the first one is some work that Alexi Amundsen did when he was a postdoc here in Cambridge with Venki Ramakrishnan, and another postdoc, Xiaochen Bai, who's now in Dallas, working with George Scherers, worked together on these bovine mitochondrial ribosomes that Alexi had worked on for about 2 years, trying to purify them and crystallizing them, because that's how lots of structures was done before the power of the single particle cryo-EM became suitable for tackling it. And he never got it very pure, because when you try to purify ribosomes from mitochondria, there are not many in them. You get all the ribosomes from the cytoplasm mixed in with it. And so this prep turned out to be about 80% mitochondrial ribosomes, 20% cytoplasmic. There's no hope of crystallizing it. It'd all get mixed up. So they processed this using Scherers' software Relion that he developed, following on from his early career in Madrid with Carazzo working on XMIP. And Scherers had had a number of initiatives that he brought with him into Relion. And one of them was 3D classification. So what they did, this was Alexi Amundsen and Xiaochen Bai, they processed images like this and got a model like this that was low resolution, 10 or 15 angstroms. But then you asked the software Relion to do classifying these, and they asked for 6 3D structures and then let the system go sorting itself out. And it turns out one of the major classes, about 30% of the structures was cytoplasmic ribosomes. There was some sort of junk, and the rest of them are indeed the mitochondrial ribosomes they wanted to see. Some of them intact, but some of them are just the large subunit. And also the ribosomes do structural changes, ratcheting and so on. And so one of the other features that Relion brought in was the ability to select a region in the 3D map and do focused determination of the orientation and position, and then get a better map of the part that you use to do the orientations. And then you could then focus on another part, say the small subunit, and get the orientations for that, and then get another structure, and then you put them together later on. And when they did that, they got structures like this, and they were able to find all of the RNA and all the protein subunits in both the small and the large subunit. So this was a combination of methods, and all of them depended on the cryo-EM. You couldn't get crystals, there were structural changes, flexibility in the structures. But if you look at the density map that they got from this, you can see it's really a nice, beautiful, 3 angstrom map. The density, the features you see are consistent with that. This is a little bit of Watson-Crick RNA double helix with 3 stacked base pairs like this, and then a top view of one of them with the 3 Watson-Crick base pairs here. And then that's an alpha helix from one of the polypeptide chains, and then 2 beta turns here with side chains quite nicely resolved. So that's one of the really good examples, an impure specimen that has multiple mixtures of states and flexibility. And that brings the power of this cryo-EM, where you're looking at images with really good detectors for recording the images and then extracting the information from it after that. So another good sample, which was even more difficult than the ribosome, was the spliceosome. Now, this is work done by Kelly Nguyen, who was a PhD student with Kiyoshi Nagai, also here in Cambridge. And until that point, from about 1990 till 2014 or 15, Kiyoshi Nagai's group had only made crystals and done X-ray crystallography, starting with 1 subunit, then 2, then 6, then 8. And each time they made a bigger and more complicated structure, the resolution got lower. But Kelly noticed that the cryo-EM was developing a lot of power, and she was the one who initiated it. Now the group only does cryo-EM. This was one of the earlier projects on the U456 tri-SNRP, and they got 3.7 angstroms using the full power, classification, flexibility, focus refinement. And you can see this is really quite a detailed model with many proteins and RNA molecules in the spliceosome. And now, of course, the group has gone on and done multiple 10 or 12 different states. So they have now a complete picture of how the spliceosome works. But this was the first map that they published, 2016. And if you look at some of the density, it's not quite as good as that ribosome map. Here is a piece of alpha helix with just resolved side chains, so a little bit of double-stranded RNA, and then a single-stranded part at the bottom. Bases are not quite resolved because they're 3.5 angstroms apart. This is a 3.7 angstrom map. But it's another good example with much more flexibility, much bigger structural changes. So a third sample is mitochondrial membrane protein complex 1, which is a very big, probably the biggest complex, 1 megadalton. And images like this were obtained from a specimen that Judy Hurst brought over from another MRC unit, MRC Mitochondrial Biology, to Cambridge around about 2014. And within 2 or 3 months, Vinoth Kumar, who was a postdoc in our group, Shaipeng Ju in Judy Hurst's group making the protein, had got this map at 5 angstrom resolution showing the 8 iron-sulfur complexes and 76 transmembrane helices, a complete picture of the molecule, not enough to fit amino acids into the sequence, but enough to see the general structure of it. And the way complex 1 works, you feed electrons in at the top with NADH, they flow down this iron-sulfur chain and reduce a quinone in the membrane, and then there's a structural change. So this is now the topic of future work. But with this first map, this is now 2014, at a lower contour level, you see the detergent lipid belt that was used to solubilize it and extract it from the membranes. And then about a year later, they got a better map at 4 angstroms by just collecting more data and doing more refinement, more focus. And in this, they were able to identify all 45 different polypeptide chains in this 1 megadalton complex. You can see now the iron sulfurs are a Pauling Corey model. The blue is about half the mass of the structure, so 16 core subunits that were helped by an earlier structure from Leo Sassanov in that same MRC mitochondrial biology unit from a thermophilic Thermophilus bacterium, about half the size. So they were able to use the information from that bacterial thermophilic homologue of complex 1 to get a start on interpreting it. But all of the red subunits, the red polypeptides, alpha helices, they're all supernumerary subunits, 29 of them. They came only from the cryo-EM map. And they were able to, and then Leo Sassanov, who'd been doing X-ray work, for example, on this, the thermophilic bacteria, he then switched back to doing cryo-EM. And so both Judy's group here in Cambridge at an MRC unit and Leo Sassanov in Vienna now are doing lots of great work on mitochondrial complex 1 and other structures, as are other groups in Germany and China and so on. So this is another example without, they did have crystals, but they were only part of the protein and not very 10 angstrom resolution. So this is a third example. Without the cryo-EM single particle work, you wouldn't have any of this. So then one other structure I thought I'd show is Miriam Koshai was another PhD student working in Martinsried in the group of Radostin Danev, who's now back in Tokyo in Wolfgang Baumeister's department. she thought it would be a good idea to look at human hemoglobin, which is a very small tetramer, 64 kilodaltons, that had been solved by X-ray crystallography in Max Perutz's group about 1968. And she took images like this, helped by a faceplate, 2D classes like this, and then got a 3D structure. This is the heme group in hemoglobin, the proximal and the distal histidine, and the whole structure. And here's an alpha helix with some side chains. So a very small structure, as well as some of these very big structures. And then the success of the cryo-EM attracted the attention then of the pharmaceutical industry. And so in Cambridge, there are 5 pharma companies who bought into cryo-EM about 3 or 4 years ago. They bought their own microscope and they use it 1 day a week each. The leaders in that consortium were this company Astex, with Harun Jyoti as the CEO, and Pamela Williams was the leader. All of them X-ray crystallographers switching into cryo-EM. And they picked 2 enzymes to get going and teach themselves how cryo-EM worked. One was beta-galactosidase, and the other one's pyruvate kinase. And they were just collecting multiple data, 1 data set a day with different ligands bound. And so at the top here, this is the overall structure, beta-galactosidase, 450 kilodaltons. Here are 3 different ligands bound in the active site, different sugars. So this top one here, I think, is phenylthiogalactose. And of course, normally beta-galactosidase, it cleaves 2 galactoses and it cleaves lactose, 2 galactoses into the 2 sugars so that the bacteria can digest it. And so this is an inhibitor of it that really binds strongly. And these were other inhibitors. And then pyruvate kinase was actually a real drug target in cancer. So these were 2 others. So it just shows now that there are now probably 15 or 20 drug companies using electron single particle cryo-EM in just the same way that they used to use X-ray crystallography for structure-based drug design. So then you could ask, that was a few examples of structures, some of which were impossible before, some of which were possible, but still now is much quicker. What about the growth of the whole field? So this one is a picture of the growth in the protein data bank atomic coordinate depositions each year by X-ray, EM, and NMR. And you can see around about 20 years ago, there was nothing happening by EM, 2 structures deposited in 1998, whereas there was nearly 2,000 by X-ray crystallography and 300 by NMR. So you could argue NMR was about 15% of structural biology at the turn of the century. X-ray was 85% and EM was nowhere. But subsequent to that, this is how it's grown. You can see X-ray crystallography still growing linearly. NMR grew and grew and grew, maybe 20% of the structures being deposited till 2007. And then it peaked, and now the NMR is used for weak ligand binding rather than de novo structure determinations. But you can see that the cryo-EM, based a little bit early on 2D crystals, but now entirely based on single particle, is growing exponentially. And one nice way to plot that is to look at the ratio of X-ray to EM, and it tells you a lot about how the method has progressed. So before the year 2000, you can see each year there's 1,000 times more coordinates being determined by X-ray crystallography. And then the microscopes got better. That was the field emission guns and the higher voltage. And then there was still maybe 200 or 300 times as many. And then the new detectors came in around about 2012, 2013. And from then on, you've got a linear on a log scale, you've got exponential growth in the cryo-EM. And if you draw a line through it, it's pretty much a straight line. And then, I've updated it recently. And so the crossover point is about 3 years from now, when there should be the same number being deposited. But of course, many of the cryo-EM structures cannot be done by any other method. So this is a really big step forward, and it means it's becoming the dominant method. So I want to show 2 other examples before moving to the sort of more recent things. So one of them is this work from Dimitri Lyonkas, who's in the Salk, and he worked as partly just to get himself going. So adeno-associated virus, single particle cryo-EM, and this is a virus often used for DNA injection or RNA and so on. So it's a vector for possible future healthcare. But nevertheless, it's a proper virus and it works in association with adeno. And they got this very beautiful structure here at about 1.9 angstrom structure, simply by doing all the things everybody else had said, gold grids, limited illumination area, the right number of movies and so on. But the reason that I'm showing this is that this is the first time that putting in a correction for Ewald sphere curvature, which happens in X-ray crystallography, but nobody had been able to get it to work before this paper. And so here you can see, this is one of these plots of the resolution, or 1 over d squared, versus the number of particles that are used in the model. And the slope of that can tell you the best B factor that describes the behavior of your data. And you remember that in the very first adenovirus structure, we had a B factor of 3000. This now has a B factor of 60. But when you put in this Ewald sphere correction, which was in Nico Grigoriev's Freeline program from 2006, but they'd never been able to get any improvement. Dimitri got it to go from 60 to 50. That's a significant improvement, higher resolution. But of course, it's already 1.93. So 1.93 to 1.86, it's very significant, but it doesn't look much in terms of the density. And they all look very nice there. So that's a really good example of how the resolutions got to such a stage that the lack of flatness of the Ewald sphere in the cryo-EM makes a difference. And I'm going to show you one other structure before we get on. And that is, several people have tried to push what resolution you could go to, although in terms of structural biology or drug design, you really don't need better than 2 or 2.5 angstrom resolution. This is apoferritin, and this is from work partly in collaboration with Thermo Fisher, who've developed cold field emitters, better detector, better energy filter, and so on. So this is apoferritin at 1.22 angstrom resolution. That's from, this is Shor Sherra's group, Takanori Nakani, but also Wachu has done it at Stanford, Holger Stark has done it. Many other groups have done really good apoferritin structures. And it's because there's 24 copies of the structure in each of these particles, and they've managed to jam in a lot into each micrograph. So they're making up for, let's say, loss of signal at high resolution by having large numbers of particles. Okay, so that's cryo-EM. It's very powerful. You can do structures not by any other method, and you can push different aspects of the methodology depending on your interests. But I thought I'd show 2 slides, one about a tomography slide from Ohad Medalia, published in 2002, showing how electron cryotomography was then. And in the rendering of the 3D image from the tomography, actin are these red or brown helical arrangements. The ribosomes are in this sort of yellowy green color, and then membranes are in blue. And that's how it was 20 years ago. But if we now take a fast forward, this is a recent paper using the similar method, but now with all the better detectors and so on, from Julia Mohammed et al. It's based from work from the Baumeister group. They've been leading in the development of the cryotomography methodology. But now you can see the quality of the map is much higher. And so when you then render it and look for these structures, you can see the nuclear pores with roughly 8 modules there. The ribosomes now can be resolved into large and subunits. You can find the orientation. These thin filaments are the actin, and the green are microtubules. So the methodology has flowed over into tomography, and a lot of people are hopeful that further improvements in tomography will allow you to do great things in the future. Okay, so then I'd like to switch now from that kind of overview and summary, showing you some of the examples of the method's achievements, to look forward a bit. So what are the outstanding issues and the obstacles to progress from now on? Obviously, the detectors, while much better than they were, you can always make bigger, better, and faster detectors with higher DQE, bigger area, and then more images per second or per minute. And that allows you to get more structures and do more work with the same number of microscopes. So that's an important area. However, making grids although the structures I've shown you were obviously successful, there are many other structures when you try and do this blotting plunge freezing method. The molecules denature, unfold, fall apart, disintegrate at the air-water interface, or all the particles are in one orientation and you can't get 3D views, or there's, just like I showed with the ribosome, mixed states and so on. And then nobody has yet really shown what are the forces on the molecules when you then plunge freeze them and blot them. So there's a lot of work to be done on the specimen area. And for that, of course, we need more microscopes so that you don't have to queue up and wait for 8 weeks to get 1 day on the microscope because of the popularity of method. And then alongside this, one idea, a new idea for making grids is to make grids that have an affinity like nickel NTA on them, rather than purifying your molecule on a column. You might be able to purify them on the, and people are working on this. So, but for all of these developments, you need more people with more microscopes, and you need daily or twice daily access. And obviously, if in Cambridge, we have to wait 8 weeks to get onto a microscope, in Brazil, it's going to be longer. So one of our ideas, which we advocated about 5 years ago, was that we really do need an affordable cryo-EM, not one costing £4 or £5 million. So this was a review Vinod Kumar and I wrote 5 years ago now. We said you can do well with national or international facilities costing 5 million, but to get daily access, you need your own microscope, at least in your own department. And for smaller structures or for higher resolution, you definitely need a field emission gun. Otherwise, you don't have enough coherence, it's blurry images and so on. So everybody in the field, either just to get their work done or to solve some of these outstanding problems, we desperately need an inexpensive diagnostic cryo-EM. And so our idea in this review, we said, why not build a 100 kV microscope with a field emission gun and then develop a better detector for it? So that was the idea. And then we wondered, and then this was with Chris Russo and colleagues in his group, we wondered, well, maybe we should check before we set the companies going to develop expensive new microscopes, even though they'll be inexpensive to buy. We better just check that there's no disadvantage to going from 300 kV down to 100 kV. And so this is a paper, Matthew Peat et al., that was published about 18 months ago, where we investigated radiation damage, which is proportional to the inelastic scattering cross-section, and the amount of information of the images, which is proportional to the elastic cross-section. And these dotted lines, sigma I and sigma E, are the theoretical cross-sections based on theories developed by Bloch and Bethe 50 years ago, but we weren't sure these theories were right. And so Matthew remeasured over the range from 100 kV to 300 kV, the elastic and inelastic cross-sections. And indeed, they are as almost exactly as predicted by the theory, because it's electrons and atoms, and so the theories are correct. And what you see here is that there's a certain ratio at 300 kV, but these lines on a log plot, they get closer together. The cross-section goes up as you come down in voltage and energy by about a factor of 2, but whereas the elastic cross-section comes down by a factor of 2, it turns out the inelastic cross-section only comes down by about 1.5-fold. So you get a gain. You don't lose anything by coming to 100 kV. You actually get a gain in information. And so here is an example then of using a 100 kV microscope. And to do that, we had to take a 200 kV one, turn it down, and then put a new detector on it, which was a Dectris hybrid pixel detector. And this is the structure of DPS, which is a structure homologous to apoferritin, but it's only got 12 subunits, so 200 kilodaltons instead of, and it's a 3.4 angstrom. And you can see the helical stretches in that structure just like before. So it works quite well. And so the plan now is that we should develop a proper, or encourage the companies to develop a proper 100 kV dedicated, affordable, inexpensive, but top quality microscope that might even produce better images than the high-end microscopes. And so I'm going to show you two like this before I finish. So one of them was announced by Thermo Fisher on the 18th of November last year, and they're calling it the Tundra, and it is a 100 kV microscope. It has, you load one grid in this loading station. Of course, this is a computer simulation. We have yet to see the actual microscope. You then carry the grid in this cartridge across to the microscope. You put it in this hole, and then you're into cryo-EM, we hope, with a really easy to use microscope. But because we wrote that review 5 years ago and no one was doing anything, and this is only 6 months ago, we actually decided we'd have to go a little bit further ourselves. So this is what we've done. So we've got a grant. We applied for a grant from the Wellcome Trust. We got some help from 2 companies, Astex and AstraZeneca, who've been involved in this pharmaceutical structure-based drug design consortium in Cambridge, and we'd helped them a lot, so they've helped us a bit. So we've bought actually 3 of these 100 kV microscopes, which are very, very much less expensive than the high-end ones. And we've put on it one of these Dectris hybrid pixel detectors, and we have a company in the UK, in York, who are experts on field emission guns, and they've been doing it for SEM for 20 or 30 years. They make hundreds of them per year. And so they have now developed a field emission gun, which we will hopefully have on this microscope quite soon. And then we'll be able to do what we did by using a higher voltage microscope at low voltage quite soon. And at the moment, we've purchased these 3 side entry cold stages that go here in the microscope from Gatan, Fishioni, and Simple Origin, and we're evaluating them all. But I think the idea is eventually you need a more dedicated cryotransfer cold stage system that would be ideally suited to fast turnaround, problem solving, diagnostic electron microscope. Okay, so that's a summary of the power of the field and how it's extending the boundaries of structural biology, but it's still got a long way to go. And the exponential growth in the field will not continue unless we can get more microscopes and more people into the field. So I'm going to finish then with an acknowledgement slide. So I've shown you work a little bit from our own, but mostly from other people. So the original adenovirus work came from Jacques Dubois, Phoebe Stewart, and then Hong Cho more recently. The mitochondrial ribosome were 2 postdocs who are now group leaders, Alexi in Stockholm, Xiaochen Bai, I've left off, he's in Dallas, in the groups of Shor Sherers and Venki Ramakrishnan. The spliceosome work, unfortunately, Kiyoshi Nagai died of liver cancer about a year ago, but Kelly is now back as a group leader here, working on telomerase. Mitochondrial complex 1, Judy Hurst is now the director of that MRC, mitochondrial biology. Shaipeng Zhu is back in China. Vinod Kumar is back in India. In Bangalore, leading the cryo-EM development in India. Miriam Koshai is now employed by Novartis in Switzerland. Radiston Danev is back in Tokyo. The Ferritin is done by a number of groups. This is the structure-based drug design from the Astex company here in Cambridge. This is Dimitri Lyonkas' work showing very high resolution on the adeno-associated virus. And then again that. So then I showed 2 slides, not really up to date, but good examples of cryotomography. And then our detector work's been done with Nicola Guerini and Renato Turchetto. Renato now has his own company in Barcelona, designing detectors, hopefully more for cryo-EM. And Greg McMullan and Wazi Faruqi work here with us in Cambridge. And this is Chris Russo's group, Katerina Naidonova and Matthew Peat, who've been involved with this, do lots of other work, but with the 100 kV project. So with that then, I'll stop, and I think I should be available for questions.
Waiting for our screen to appear on the other. Hello? I'm not seeing the video.
We have questions from the chat, Eduardo.
Okay, yes, now. Okay.
No, from the chat.
So I guess I first need to thank you, Richard, for the excellent lecture. There's a delay between the discussion and the end of your lecture, but I think that was a great view into the future and a historical beginning that was very important. But so now we're waiting for people that have a question. I have questions, but I mean those we can discuss over a beer and a pizza as traditionally.
You know, I have to say, the only reason you need the overview and the background is for people who haven't listened to talks or kept up with the field. But for us who are in the field, if you're talking about the past, the present, and the future, really, we are only interested in the future. So.
There's a delay in the video, so we're actually looking at the picture from the past. And
how much delayed is it?
Well, at least 20 seconds.
All right.
I'm lifting my arms up for the second time now. Rodrigo.
Okay, so let me start with a question. Richard, thank you very much for this excellent presentation, and I'm really interested in listening a bit more about sample preparation. How do you see the future of sample preparation? Because we know this is a huge bottleneck nowadays, in terms, like, not only in technologies, but also in terms of how much we can do. Like the throughput is not enough yet. So if you can discuss a bit more on, you know, samples less purified, how we can tackle that, how we can increase the throughput of testing different conditions, and also a bit on time resolved, like this new strategies to like fast mixing and freezing, and then what can we expect from that to the future? Yeah.
Okay, so that section that I showed in my talk about the need for affordable cryo-EM, that was section 5 in a big review that Vinod and I wrote about 2016. And we put into that review things like trends, developments, perspectives. So there's lots of things in that review, in Quarterly Reviews of Biophysics, which I can recommend to anybody who wants to do some background reading. And other people have written reviews in the past. However, it is true that specimen preparation is a bit of a problem. And one of the tables we put in that review that is very useful for understanding what happens when you prepare a specimen. So let's say you have a sample. Let's say it's ribosomes, or let's say it's an enzyme or viruses or so. And you take a little drop of the sample, blot it with the Dubois sponge freeze, plunge it into liquid ethane, and look at it in the microscope. You hopefully see something when you do, but often you see nothing. The particles that you wanted to see, they've disappeared. So the question is, where did they go? You know they were there to start with because you've assayed them on a column and you've got an optical density and so on. So one of the tables we said is that once you know the concentration of your sample, shall we say it is a 1 milligram per ml solution of an enzyme, and if you know Avogadro's number, which you do, you can calculate how many particles you ought to see in the plunge frozen image if the particles are behaving as though they are in free solution. And almost invariably, when you make a grid, you either get many fewer or many more particles than you ought to get. And that's because if it's fewer, your particles are sticking to the carbon film, or they're sticking to the blotting paper, or they've denatured or something like that. So if you get many fewer, that's one problem. But sometimes you get many more. So they've been concentrated by the blotting and plunge freezing method. And they can become concentrated either by not being sucked off by the filter paper, so it's actually concentrating them, or they're binding to the air-water interface. That's quite an often thing. And then that often gives them preferential orientation as well. So there are various ways around that. And one of the things that we and other people have been doing is if it's not a membrane protein that you're working with, so shall we say it's a ribosome or an RNA polymerase or an enzyme, or one of the specimens we worked on was catalase, which is a 200 kilodalton enzyme like this DPS. And so one thing you can do is you can add a little bit of a detergent into your non-membrane proteins specimen. And usually detergent is very mild. You can use mild detergents. You can use dodecomaltoside. In our case, the best one we found was Chapso. That has no effect whatsoever on our sample. But the detergent forms a monolayer at the air-water interface with the hydrophobic part pointing towards the air and the hydrophilic part. So then your specimen that you're interested in doesn't see the air-water interface. It doesn't see the filter. It sees the hydrophilic end of the detergent. And then the number of particles you get is exactly the number that you expect from calculating it and knowing roughly the thickness. And when you do that with 1 milligram per ml of an enzyme, say 250,000 molecular weight, it turns out you don't get, and you shouldn't get, all that many particles. So there's a big advantage in increasing the concentration, 10, 20, 30, 40 milligrams per ml. So for some soluble non-membrane proteins, that's a good thing to do. But of course, with a membrane protein, you'll usually have detergent in there already. And so one of the reasons that the cryo-EM method has been so successful for membrane proteins is because it's got detergent in it already. And so if you look at that graph that I showed you, showing you that the number of protein data bank depositions will be equal for X-ray crystallography and cryo-EM in 2024, and if you do the same plot only for membrane proteins, it was already equal 2 years ago. So membrane proteins is already 5 number of deposits per year. And that's because the specimen preparation still has problems. So, for example, we worked on voltage-gated ion channels. They absolutely fall apart. So there's a lot of work still to be done on generating better ways of making specimens. And there's lots of people working on it, but every time they try a new idea, they need to put a grid in the microscope. And so they basically need, so my view is the main thing we need is more microscopes with more access and not too expensive. So obviously in Brazil, if the microscopes were only £500,000 instead of £5 million, you could buy 10 times as many for the same amount of money. And you probably do almost as well in terms of, and a lot of the problems, even in our lab, in our group, we just need access. And by doing that, you can try different things, and then you understand more about the behavior of your molecule. Okay, so that's specimen preparation. Lots of things to be done, but every time you try something new, you have to look at it in a microscope. So my view is it'll go 10 or 20 times faster once people have more microscopes. So we've given that our highest priority. That's what we're mainly working on. Okay, when it comes to time resolved, somebody is speaking in the background. But anyway, when you come to time resolved, it's frozen. So, in order to look at it in the microscope, it has to be cryo-EM, it has to be frozen. So you can't do kinetics, but you can do plunge freezing and trapping after different, you can do mixing, you can do stop flow. There are various ways of doing kinetics that have been worked out for spectroscopy, and you can transplant those microfluidics, you can transplant them into specimen preparation for cryo. And it's fairly early stages for that. But my current view is there's still lots of structures we need to know, and not so many that you need to know about intermediate. So I think the big future is basically standard electron cryomicroscopy as a method of structure determination, drug-ligand interactions, and then the kinetic aspect, time resolved, trapping things, will be an important part, but it'll be a minor part of that.
So, Richard, thank you for your nice presentation. I have some questions here. Please, Professor Marcos Farina, feel free.
Okay. Marcos has his hand up, I see.
Farina,
Hi.
você está sem áudio.
I think.
Sem áudio ainda, Farina.
Yeah, go ahead. But I think you might be muted, are you? You are muted.
Farina, ainda não. Não estamos te ouvindo. No.
There's a red symbol in his window on my screen.
Yeah.
Mutar de novo seu microfone, talvez tenha algumas erros.
Aqui para mim tá.
That's okay now.
Okay. So thank you very much for this wonderful presentation. I would have many questions, but I have two. One is about apoferritin. Should it be possible to have this high resolution with ferritin, with the crystal inside ferritin, the ferrihydride crystal inside, or should it be difficult because of the fact that it's a crystalline structure and it should have to do the contrast is dependent on the orientation. And the second question is a more almost philosophical one: how to guarantee the resolution in a range, in a length scale that you cannot compare the images with any other technique? Should it be dependent only on the Fourier analysis? Could you have, for example, a systematic error in the sample preparation that you cannot guarantee that it's not corresponding to the real structure?
Yeah, okay, so thank you very much for those are good questions. As far as I know, no one yet has taken images of ferritin with the iron inside it. But usually the way it works to get high resolution structure, you need many thousands of images. So you're averaging them, and the iron does nucleate at different sites inside the apoferritin core. So it might well be that if a structure for ferritin was done, the orientation would select. If you apply the 4-3-2 symmetry, that's the normal symmetry of the capsid, then the iron that's inside it would be smeared out and would have the same 4-3-2 symmetry. But if you were to do the structure of the ferritin with the iron in it and then apply and then remove the symmetry and let the refinement programs proceed, you might then get a structure that wouldn't be quite such a good resolution, but you'd see all the subunits, and then it would be oriented such that, let's say, the most occupied site for the iron would be in one position each time. And then you might well, I think it's quite a good idea. You should persuade someone to do this or do it yourself. And probably it's better if you start with ferritin that has only a small amount of iron in it rather than a large amount. And you see this in the images immediately. So actually you could just take ferritin and then divide up all the particles into the particles that have a lot of iron, a medium amount of iron, and a small amount of iron, and then do the image processing in that way. And then I think you would find out, indeed, you'd find out something about how the iron binds to the, I think it's internal aspartic and glutamic, perhaps, that are involved in that. But no one has done it, so it would be a good thing to do. And then the other one was this more philosophical question. I guess the question is, can you get the wrong structure by cryo-EM? And with other methods, for example, with X-ray crystallography, there's 170,000 sets of coordinates deposited now. And most people cannot remember them. There are too many. But we remember all the structures that were wrong. And the same is true of NMR. We remember the ones that were wrong. And they tell you about what are the pitfalls and the problems with the method. So the good thing about cryo-EM now is that the resolutions have got sufficiently high that when you look at the density, once it's beyond about 3.5 or 3 angstroms, you can see the polypeptide chain with the side chains. And so that is a really good, strong, independent confirmation that you've got it right. But for example, if you have a structure that has no symmetry, like a ribosome, it's a C1 structure, and supposing you did image processing and you said, I think the structure is C2 or D2 or icosahedral, the programs will give you a structure that's C2, and they'll be wrong because they'll be mixed up. There'll be superpositions. And so I think you do need to have some idea of what it is you expect to see in the structure, unless you get to very high resolution. And this was a problem between about the year 2000 and 2012, when everyone expected the structures one day to be better, but they weren't good enough yet. So then quite a few people who were not very critical and they didn't ask difficult questions, they thought their structure was fantastic and they tried to publish it. And there's a famous one which Maren and I were involved with a discussion on HIV envelope glycoprotein. The people doing it, they were not cryo-EM experts, but they were medical researchers from Harvard. And they first tried to publish a paper saying this is the structure of the HIV envelope glycoprotein at 2.5 angstrom resolution, when no one else was succeeding in getting anywhere near that. And it turned out it was completely imagined. They put a model in and then refined it, and it went round. They had the wrong belief, and they didn't do critical tests. Now there are many, many tests. So now you couldn't do this. You cannot make that kind of mistake. So the field has raised its level in terms of validation and criticism. And so now I would say, unless you're at, let's say you were only at 6 or 7 angstroms, and then if you are, you have to ask, why can't you get to high resolution? There's probably some problem. The specimen is falling apart. So I think we now have a lot of tools, and you can know when you're right because you see the structures that you expect to see. But there may be a small group of structures that are at lower resolution, and those you could probably still misinterpret. So I think just like in any other field, X-ray, NMR, you have to look for other evidence and make sure that the structure you get agrees with all of the prior knowledge from other areas. So I think philosophically we're now on solid ground. We don't worry about, it would be nice to have 1 or 2 big scandals in our field, but we haven't had any recently. We've had some incipient ones earlier, which we managed to avoid, but there have been quite big, famous problems. For example, metallothionein, which was the work of David Stout in Scripps, was completely wrong by X-ray crystallography, and the NMR people got it right. Similarly, I think David Eisenberg got the right chain trace in Rubisco, an enzyme from plants, but he got, instead of the N-terminus to the C-terminus, he had C-terminus to N-terminus. It was just flipped. So it's not such a serious problem, but all the side chains were in the wrong place, and that was corrected by another group, and then, of course, they noticed there. So there are plenty of ways to make mistakes, but there are also plenty of ways to check nowadays.
So, Richard, you have a time for more one question. Dr. Kildare, please.
Professor Henderson, thank you very much for your presentation. It was really nice to know that we have hope for the cryo-EM community using less expensive instruments, which, as you said, is delaying the perfection of sample preparation, which I believe that is also something that will contribute to cellular cryo-EM also. Once we have less expensive instruments. But on the side of the expensive machines, do you think that there's some space in the future to combine energy-filtered EM, TEM, with the cryo-EM strategies to localize ions bound to molecules?
Yeah, so, I mean, one thing that would be very nice, but there is no hardware to do it. If you could, so at the moment, we take images either without an energy filter or in tomography or something, we use the zero loss energy filtering. So you get one beautiful image or one beautiful movie or thousands of them that are really nice and contain lots of information. However, if it's zero loss, all the energy loss images, 10 electron volt, 20, 30, 40, 50, they're all thrown away. So what would be really nice would be to have a new type on the bottom of the electron microscope. So have your gun, the specimen, the beam comes down, and then you have an energy filter, but instead of it going with a window just to one detector at one energy, you have several windows, and the images go to 4 or 5 different detectors. So you get zero loss, 10 eV, 20, 30, 40. And at the moment, no one has been able to think of a practical way of designing an energy filter that would send the images at different energies to a different detector. You can do it by STEM, by scanning, but then you lose the phase contrast. So what we want is phase contrast imaging, in which, and in principle, you can draw it on a piece of paper, but translating it into a new piece of hardware would be quite difficult. And then, if you can do that, then in principle, although the signal to noise will not be very good, in principle, you can find where are the iron atoms, calcium, and things like that. And I did just read yesterday. I've been. In addition to electron cryomicroscopy, there is still the field from the synchrotron people of X-ray microscopy. Now, I certainly showed, and everybody knows now, that the information you get in X-ray microscopy by phase contrast compared to electron microscopy needs a much higher dose. If you measure it in terms of radiation damage, it's about a factor of 1,000. So no one is trying to do X-ray microscopy at 2 angstrom resolution anymore. However, if you say there's this factor of 1,000, you could do X-ray microscopy instead of at, say, 2 angstrom resolution. You can think of it as 2 nanometer. So that's 10 times bigger voxels. That's 1,000 times lower dose rate. And actually, it doesn't work at 2 nanometers, but it kind of works at 5 or 10 nanometers. And so with X-ray microscopy, you can do simultaneous imaging, particularly there's a paper, I think it's this year, 2021, by Chris Jacobson, who is the leader in X-ray microscopy. And he has a 3D image of, I think it's euglena, of a single-celled organism, which is about 10 or 20 microns. And so you can use bigger objects. The resolution is probably only, I don't know, it's 100 angstroms or 200 angstroms. It's low resolution, but he's got images of all the different elements. So it's a low resolution image, but it gives you the general idea. So there are two ways forward. One is that somebody develops a new type of energy filter that allows you to simultaneously record phase contrast images at different energy ranges. And the other one is the X-ray microscopy community are just beginning to invest in a new generation of synchrotrons. Most of them, the only one that's working at the moment is in Grenoble with the new high brightness beamlines. But over the next 10 years, there'll be developments in synchrotrons all over the world. They're all upgrading, and they're all focused on X-ray microscopy of cells and tissue at lower resolution than EM. So I think everybody now knows what area of biology their method is most suitable for, but still it needs more investment and more time.
Okay, thank you very much.
Okay. We've done our hour, I think, but.
Okay, thank you. So you have one more question here on the chat from Andre Ambrosio. So what would be your main advice for developing and especially scattered community of novel cryo-EM user in Latin America?
Yeah, that is also a very good question. I think the key is there are many groups who are very skillful in biochemistry, who are in Latin American countries, different countries. So I think that in the short term, the best advice would be to, if you're interested in the structure of the thing you're working on, develop a collaboration with somebody who has bought all these expensive microscopes and they want good projects to do it on. And then that would be the first general advice. And obviously it's better to pick someone close to you, but there are now many, New York, in the UK, we have EBIC at Diamond, there's ESRF in Grenoble, there are many cryo-EM centers now, and I think there is one CRYOS, is that right, in Brazil? So you could go to so the best advice for people who have got good projects and would like to do is to find a national or international center and then find a collaborator to get you going. But if that work is very successful, you definitely want to buy your own microscope. And at the moment, you can order one of these Thermo Fisher Tundras, and they are about $1.2 million. They're still about 5 times, they're still expensive. We're hoping this gel system will be about half that cost, so about £500,000, say $600,000 or $700,000. And so I would keep an eye on that over the next year, and then obviously you have to get the money and then buy one and have it installed locally. So we think that there'll be, over the next 10 years, there'll be more of these expensive high-end microscopes, but probably after 10 years, there'll be just as many entry-level microscopes that may well be able to do not quite so automatic and not quite so many images per day, but for diagnostic work or for small projects, we're working perfectly well. Yeah, so the bottom line is the national or international collaborations to start with, and then based on the success of the work and the promise for the future, get a grant and buy into one of these low-end cryo-EM microscopes that are going to produce fantastic images, actually. So those would be 2 good ways forward.
Thank you, Richard. So you finish here, Marie, if you have one more.
Just thank you. And there are a number of offline issues that I need to talk to Richard about, but that's not of general interest right now. It's advanced stuff. Thank you very much, Richard.
Okay, so
since I introduced you.
I have to go away for a while, but I will rejoin the meeting and listen to one or two of the other talks on the other channel.
Okay.
Thank you very much.
Thank you very much.
Thank
We're
you.
very
Thank you
well.
very much.
Very grateful.
Have a nice day.
Bye-bye.
Bye-bye.
Bye then.